You don't know what you got till it goes, till it's gone. You don't know what you got till it goes, till it's gone. I wish somebody would have told me, babe, someday these will be the good old days. All the love you won't forget, and all these reckless nights you'll regret. Someday soon your whole life's gonna change. You'll miss the magic of these good old days.
You know I'm back, like I never left. Another sprint, another step, another day, another breath. Been chasing dreams, but I never slept. I got a new attitude and a lease on life is a piece of mind. Seeking to find I can sleep when I die. Want a piece of the pie, got the keys to the ride and shit. I'm straight. I'm on my way. Get up my way. I'm running late. What can I say? I heard you died twice. Once when they bury you in the grave, and the second time is the last time that somebody mentions your name. So when I leave here on this earth, did I take more than I gave? Did I look out for the people, or did I do it all for fame? Legend is Exodus, searching for euphoria, trudging through the mud to find the present, no ignoring. I got 20,000 deep up in the street like we some warriors. My mama told me never bow your head. Whoa.
I feel glorious, glorious. Got a chance to start again. I was born for this, born for this. It's who I am, how could I forget? I made it through the darkest part of the night, and now I see the sunrise. Now I feel glorious, glorious. I feel glorious, glorious.
I'm feeling glorious. The crib looking victorious. Oh yes it is. You know that we've been going it since we hopped out that DeLorean. Yeah we went on guard. Things are just.
Is the magic time?
Let's see. Almost. It's 1 minute. I could have learned more names.
I mean, depends which
Oh.
one is accurate. This is one minute.
This one is better. Yeah, that one is digital. No, that one is analog. This one is better.
Well, I mean, you can have an analog one that synchronizes to, you know, to the time reference, but
Yeah,
it isn't.
but now it is.
Now it is. All right, it's the magic time. Ready?
Ready?
Welcome, EECS16A. Woo!
It always sounds like ooh.
Oh, by me?
No, by them.
Oh,
Yeah.
you know, it's like some of them, it's like the first class, and they just don't know how to take it. You know, it's just like, what? We'll have to do that for the rest of our kind of like every lecture at Berkeley.
Are they kidding us?
Are you kidding us?
Every day we
Like,
have to put our arms up in public.
You know, the thing is, this is noon. First of all, super appreciative that you're talking while I'm talking. But now I'm just going to talk. Super appreciative that you're here. The experience that we have teaching you in front of you is, for us at least, significantly better than not having you. So thank you all for coming. And this is, I think, the best way to catch up with lectures, I think, right?
Definitely.
Like, you just put this hour and a half, and then the next day, I think they have discussion.
Yep.
Yep, they have discussion. And what day are you going to discuss?
What was in lecture?
What was in lecture?
Yeah.
And so I guess and when is the video is up?
The video is after this, whenever we have time.
Whenever we have time, we upload it, and so it's may not have time to watch it before discussion. And so discussion is not a very effective interwebs, folks. So really, just show up in class. That's really the best. Just keep coming.
Tell your
And
friends.
I know
to
I'm
come.
speaking to the choir
those
here,
that are here.
to those that are here, but I'm also speaking to the one recorded that will watch it maybe in a couple of weeks. And so
Too late.
too late.
After homework.
Ah, good stuff we're having today. You know, this is one of my favorite lecture. You know,
Oh, yeah?
it spans so much stuff. So much stuff. The span is really
Spins. Very
and
good.
really transformative. And you know, but it depends on if it's linear or not. You know. So.
Always.
Okay. So last time we did some proofs. We just started. I'm going to do another proof today. Thank you. I'm going to do another proof today, and then we're going to talk about linear independence. So both independence and dependence. Both are, you know, very large two topics. And then we're going to go talk about matrix transformations, which is also another pretty good one. And I'll show you some pictures and all that kind of stuff, and it's going to be fun. So do you remember what span is? That was last week, so obviously not. Just to remind you, right? Because it's there was the weekend, and you know, like stuff we do on the weekends. Don't want to talk about that. Oh, Imagine Dragon concert was amazing. It was really great. And then Macklemore, I don't know if you know Macklemore, was just like a warm-up. It was superb. Superb. It was amazing. So highly recommended. Okay, so span. Span, column space, range, all this good stuff. I'm just going to rotate here. I'm just going to look at you. It's all the same, pretty much, the same definition. Sometimes we say the span of the columns of A. We said that when we say a span of A, somebody's going to cry. Okay? Don't say span of A. You can say the column space of A. You can say the range of the matrix A. But you want to say the span of the columns of A. Okay? So the span of the columns of the matrix A is the set of all vectors B such that AX equals B has a solution. Give me a B. Thank you. AX equal B. Is there a solution? Yes. That means that B is within the span of the columns of the matrix of A. If there's no solution, then it's not within the span. Okay, so it's actually very useful. Remember we talked about tomography? Had to mention that one. Remember we talked about tomography and we said, oh, there's infinite solution. Oh, there's unique solution. Oh, there's... And then I kind of told you, oh, how do we do this? How do we see this? And oh, we can do Gaussian elimination. But you know, from that, all this Gaussian elimination, I mean, really, if we could analyze the matrix and realize what the span of that matrix is, we can tell a lot about that system it represents and what it could do and what it can't do. So it's a pretty important concept. So it's really all the set of vectors that can be reached by all possible linear combinations of the column of A. Because when we multiply A times X, we are combining the columns of the matrix A, and we're reaching something. And remember, you were there, right? Remember the soccer watcher over there? And when we had all these vectors and we reached it, and it's like, we had this, like, I had this long fiberglass, you know, mast, and like I was able to touch, you know, the students here. And the reason I was able to touch because you were in my span of those two vectors. And then you can have a more mathy definition. If reverse E, remember what reverse E? There exists actually. If there exists a vector X such that A times X equals B, okay, so there exists one such that this happens, then B is within the span of the columns of A. B, that means that by a linear combination of the columns of A, I can reach B. Is that always guaranteed?
No.
No. No, it's not always guaranteed. Is that a good thing when that happens? Well, depends. Depends. Let's say it happens when, then a nuclear bomb just lands on some, just like, because it's not a good thing. Depending on who sends it, I guess. Okay, so I guess the answer is really depends. So I want to do a proof now that relates to span. And I'm going to invent a theorem. It's called 16A span theorem for this particular matrix. Okay, so it's not really a theorem, but it could be, but it's not very general. It's not a very general theorem. But it's good enough, I think, for us to go through the steps that are required to prove this property. I says, well, let's take those two vectors, 1, 1 and 1 minus 1. And I'm going to say, well, the span of these two vectors, so any linear combination of these two vectors, is the entire R2. I kind of showed you last time with the Vegemite. Yeah, that's similar, right? All the spreading stuff. And then we walked around and we did this. But I didn't really prove it. And so we really want to prove it using the definitions of a span. Okay, that's what we want to prove. This is the case. And last time I showed you kind of a concept of a proof, right? Like we proved that if you multiply a linear equation by a non-zero scalar, then you don't change the solution, right? And we had this was a type of a constructive proof that we went through, so we're going to go through a constructive proof in this particular case as well. So same, but different. But now we want to show something slightly different. Okay, so what the first thing that you do when you're required to prove something? It's good to kind of write to yourself what you know about the problem. And then from that, what you know, then you can reach what you need to show. Okay, by manipulating all sorts of stuff. So use the stuff that you know. Okay, so what do we know in this case? I don't know. Well, we know the definition of a span, right? The definition of a span is that the span of these two vectors is effectively some vector v that is the linear combination. So there exists some alpha and beta that if you combine those two vectors, these two, then you would get v. So it's a linear combination of those. And so this is a set of all v's that satisfy this linear combination. That is really the span by definition. Okay, that's what we know. And what we need to show is we need to show that the span of these two vectors is R2. Okay, so there's things that we know, and then there's things that we don't know, that we need to show. And how do we go about it? I mean, let's say I gave you, instead of R2, I would tell you, oh, is the vector 1, 0 within the span of these two vectors? What would you say? You'd say yes, but why? How can you know that? Just slowly, but surely.
Multiply the first vector by 0.5 and the next vector.
You multiply the vector by 0.5 and add to the other vector by what's okay, but hold on. Before you do that, you had to solve something. Like I know you solved it in your head. What did you solve?
I solved basically alpha.
You solved for alpha, and you solved for beta, right? So if I gave you 1 and 0 as instead of R2, and I asked you, is 1, 0 within the span? What you'd go is you form a linear set of equations, right? What is alpha and beta such that alpha times 1, 0, 1, 1, and plus beta times 1 minus 1 equals to 1 and 0, right? That's what you would solve. But now, it's not this 1, 0 solution. I want to prove for the entire R2. So what do we do then? Yeah. Oh, replace 1, 0 with a parametric explicit solution. All right? Before, we had, remember with the proof last time, we picked a solution, y0, right? Like we picked that one. And say, oh yeah, x0, y0 are, these are solutions. Well, now we can say, okay, let's pick some parameterized vector in R2 and then see if we can have an alpha and beta such that we can reach it. Okay? Now, because it's parameterized, it's specific solution, but it's parameterized, then if I can show for any, for any vector, let's pick, for this particular case, I don't know what I usually pick. I pick like a B, vector B. Okay? So B1, if I can reach this vector B, then yeah, then I'm within the span. So I know I can find. Give me some value, then I will give you what are the alpha and beta to reach it. That's kind of what I want to show. Does that make sense? Well, let's just go through it. So the concept of the proof is we pick some specific vector B, not 1, 0. I mean, I could do it for 1, 0, and then 1.1 and 0, and then 1.2 and 0. And it doesn't make sense, right? I have to prove it for everything. So I'm just going to prove for a parametric B1 and B2. Now, is B1 and B2 in R2? As long as B1 and B2 are reals, yes, it's in R2, right? And we want to show that this vector actually belongs to the set. Okay? Okay, that's what we want to show. So I want to show, is there a linear combination that would do that? Okay. So what we need to solve is for some linear combination of these two that would reach B1 and B2. Okay? So some alpha times 1, 1 plus beta times 1 minus 1 equals B1, B2. Now, this is not a very complicated example, and the reason I'm showing you is again, it's to go through the process, first of all, for you to understand what span is. And then the other one is to kind of show how you go about proving things, right? We're going to practice a few of these. Okay. How many equations are there? There are kind of 2 equations. What's the unknowns? Is B1 an unknown? No, we know it. B1 is we set it. Okay, we set B1. And B2, we also know. These vectors we know. And so the only things that we don't know are alpha and beta, and we want to find those alpha and beta such that they satisfy that. Okay, so these are unknowns, and these are knowns, and the knowns are within R2. So what I need to do now is put it in a form where I can solve it using Gaussian elimination. Not the game, but the algorithm. That's right. That's right. You repeat something enough times, it becomes the truth. Unfortunately. Okay, so let's put it in a form that we kind of know, right? Like AX equal B kind of form. Okay? Where instead of X, we say like A, the parameters, right? So what is the form that we want? We want to put it kind of like in a matrix multiplication form, like something like this. That's equal this. That's kind of the form. And once we put this in this form, we can, create the augmented matrix and solve it using Gaussian elimination. Okay? Okay, so what is this form? First of all, what is the stuff that we know? So this one is B1, and this is B2. Okay? And then what do we don't know? Usually we put the don't know stuff in this nice place. Alpha and beta. And now we need to construct this matrix that multiplies that such that we get the linear equations. So what would be that matrix? The matrix would be 1, 1, and 1, negative 1. Now, why did I actually do this? Well, you can kind of see alpha multiplies 1, 1. And when I do like this, like that, like this, like that, my thumb only touches the first column and it touches alpha, right? And then my pinky finger, like this, like that, right? Touches the second column, okay? All right, so now I can solve it, right? Now, I put it in this form, and I can even convert it into Roman handwriting. Slowly, yep. So I put it in this form, and now I can solve it. Is that going to be a proof? How do we solve this? We said Gauss elimination, not the game, but so let's just try to solve it. And I'm just going to start. I'm going to start the solution, and then I'm just going to go in a like a fast mode and skip some parts, because you know how to do Gaussian elimination. So you just go this, copy 1 minus 1, and then you put here, what do you put here? Yeah, think about it just a second. Yeah, it's B1 and B2, right? That's the solution, right? So yeah, that's the augmented form. And then what I'm going to do is I'm going to take the second row and subtract I'm going to subtract the first row from the second row. Okay, so I'm going to do that. I'm going to do 1, 1, B1, and then 0, and then minus 2, and then B2 minus B1. Right? Then I'm going to divide by 2, by minus 2. Let me just do it kind of in a nice way. Okay? I just sped that up, and now I need to eliminate and do all this other stuff that I did before. And so basically, you go through the step. This is the first step, second step, and then third step that I just showed you. And then now you do back substitution. And when I do back substitution, I would get this final result. And what does the result actually mean? Yeah? So I know alpha. What is alpha? Alpha is B1 plus B2 over 2. Beta is B1 minus B2 over 2. So now, give me a vector, 1, 0. Well, you substitute B1 with 1. You substitute B2 by 0. And you get the solution for alpha and beta that would reach. That would reach that vector. So any vector now in R2 I can reach. Woohoo! Yeah, I've got an equation now, and the equation always is true, right? Give me some vector in R2, you got a solution. Hence, I can always find a solution. KQED, right? Proven. So for every B in R2 can be written as a linear combination of those two vectors. So that means that B is within the set, okay? And then that also means that if I want to find basically the linear combination of these two to reach this would be B1 plus B2 over 2 times 1, 1. B1 minus B2 over 2 times 1 minus 1 will reach B1 over B2. That is true. Done. Proven. Okay. That's nice. That's nice. And this is a constructed proof. Okay, we constructed the solution, right? From what we know to want to show, we found we created an explicit solution and we solved for it, and that is our proof. I'll show you some other cases where we're going to do something else. Okay. Any questions? Yeah. No, actually, no, I don't need to prove. So the question is like, do I need to prove that the span is more than R2, or no. In this particular case, right? Like we knew what we wanted to show, and what we wanted to show is that B can be reached. How do we show that B can be reached? We find a solution to reach it. Okay, that's what we've done, and so that does enough in order to prove that it can be reached. Right? There's no if and only if kind of argument. Okay. Now I want to talk about the department of redundancy department. When we have some linear dependence. Oh, by the way, I forgot, there's an announcement. There's no class tomorrow. Don't forget that. Okay? No class tomorrow. And on Friday, I'm also having something going on, so no class on Friday. Okay? Just remember that. Well, let me write it down. No class tomorrow. How do you spell tomorrow? Like this? Double M? Double R? I always forget. The only things I know how to spell is diarrhea, but which is actually quite hard, but there's a song. So that's hard. Of course I can. Search diarrhea is hard to spell. But it's easy to smell. All right. Yeah. Yeah, there's just no class tomorrow. Okay. Like everything else is fine. My point is that was a redundant. That is a redundant point. And so that's kind of what we're going to talk about when we talk about linear dependence. Okay, this redundancy. Because recall that we had this matrix 1, 1, 1 minus 1, and we call this, let me give you attention now. And we give you, what did we give you? I lost my train of thoughts. Oh yeah, and then I said, oh, can I put all my Vegemite on the cracker using this, right? And so yeah, I have two vectors, but when I spread on A1, A2 is on the same line, so it doesn't let me get out of the line. And so the question is, if I want to find a point, some point here, what does that mean? Right? Like there's infinite solution. Why is there infinite solution? Well, because I can go in this direction a long way and then go back in that direction the same amount. Or I can go first here with, I don't know, this much, and then I can add the other one backwards. So there's infinite solution. I can just go 3 times A, minus time, just combine them with infinite ways. That's why there's infinite solutions. If I have something on the line, if I have something outside of the line, I can never reach it, so there's no solution. Now, the thing is, what I'm also saying is that A1 and A2 are linearly dependent. Okay. Well, what does that mean? Well, what it means really that I can express A1 in terms of A2 and vice versa. Some scalar multiplication of A1 would result in A2, and some other scalar multiplication of A2 would be the same as A1. Okay? So in this case, A1 equals minus A2. So they are dependent. Okay? That's the kind of the definition. But it's not really a definition, so we'll have to go and mathy define it. Okay? So you're going to define it in a nice mathematical way. And pay attention here. That's going to be on the quiz tomorrow. How many emails we're going to get for that, Anna? Ed comments? No.
Many.
Maybe. Yeah. The people watching the lecture in 2 weeks will be like, oh, there was a quiz on Wednesday. Right? Because it's going to go also like a 2x time, so it's like, there's going to be a quiz tomorrow. Right? And so.
Poor Austin.
Yeah. Okay, a set of vectors. Now we're going to take a set, A1 all the way to AN. Okay, so n vectors. Those vectors are in R, let's say Rm. I actually did not define that, but What's the length of the vectors? M, how many? N. Okay. They say that they're linearly independent if there exists a set of scalars that belong to R such that, whoa, what is that, Mickey? You put the sum here and all that kind of stuff. Whoa. That looks complicated. But here what it is, right? If you can express some vector AI, so one of these folks, let's say A2, as a linear combination of the rest of the vectors, that's really what it says. The AI can be expressed as a linear combination. So some alpha times alpha 1 times A1, alpha 2 times A2, alpha 3 times A3, alpha 4 times A4, and so on and so forth. So it's a linear combination of all the A's except its own. Okay, if we sum all the other ones, if you can do that, that means that these are a linear dependent set. Okay, these vectors are linearly dependent. Okay? Do you want an example, specific one? I think it's easier. Let's do an example. So, for example, let's just randomly pick vectors. Let's say A2 is equal to 3 times A1 minus 2 times A5 plus 6 times A7. If I can write that, that means that this set, A1, A2, A3, A4, A5, A6, A5, A6, A7, are linearly dependent. That set is linearly dependent. Because I can find a linear combination of those 7 vectors such that I can express one of them. Is there an A2 here? No. If there was an A2, then it's pretty obvious. Right? If A2 was on this side, it was pretty obvious because all the coefficient could be 0. Right? Okay. So that's really, yeah. Oh, you know what? You're absolutely correct. So this is M. This is N. Thank you. Let me correct the future. Okay. Now, hold on. What does it also mean? Okay, so when I write this, what does it mean in this form of equation? Okay, AI, what is I? I equal 2, right? So in this case, I equal 2. And then we sum over what values? In this case, M equals 7. So we sum over what values? 1. We sum over 1. Let's say we sum over the j's, j not equal I, right? So not equal 2. So 1 is not equal 2. So yeah, we add it to the sum. And then what is A1? A1 is 3, yeah. For this specific case, A1 equal 3, yeah. What about j equal 2? Do we sum over j equal 2? No, right? Because it says j not equal I equal 2. Okay, so we don't. So we skip it. And then we say, okay, plus A3, alpha 3 times A3. What is alpha 3? 0. Alpha 3 is 0. Okay, what about 4? 4, yeah, it's not equal to 2, so we sum over it. What is alpha 4? Alpha 4? 0 also. Okay, then we sum over 5. J not equal 2, yeah, so j is 2. 5 is not 2, yeah, so we sum over it. What is alpha 5? Minus 2. Minus 2. Right? That is alpha 5. And what is alpha 6? 0. Alpha 7? 6. Okay? So basically, this equation, we put numbers for it for this case. And the numbers are alpha vector equal to 3, for j equal 1, alpha 1 equal 3, alpha 3 equals 0, alpha 4 equals 0, alpha 5 equals -2, and so on and so forth, okay? That's really what it says. And you know what it also says? That AI is a linear combination of some vectors, right? What does it mean to be a linear combination of some vectors? To be within the span of them. That also means the A2 in this particular case is within the span of A1, A5, and A7. Does that make sense? Okay. All right. So AI is in the span of all the alpha j, all the AJs. Okay, that's what it means. Yes. Yes, it is also within the span of A3 with coefficient 0. Yes, that's right. Okay, so the question is, are these linearly dependent? Think about it. Are these linearly dependent? I got 3 vectors of length 2. If we want to show that they're linearly dependent, what do we need to show? That if I take 2 vectors, there is a linear combination that can reach the third one. That's really what it means. Okay? That's really what it means. If I take 2 vectors, I can reach the third one. Can I write it down? Let's pick the first 2 and show that we can reach the third. So I need to find some alpha and beta such that this times alpha and beta would be equal to 3 and 1. Basically 1 minus 1, 1, 1 minus 1 times alpha and beta equals 3, 1. Right? That means that there is a linear combination that I can reach this. Is there? Is there? Hell yeah. We just solved it. We solved it to the general case. We solved this exact problem. 1 minus 1 alpha beta to B1 and B2. We solved it for all R2. Okay? That's what we did. Right on it?
Yeah.
I know. We did. So we have an equation even. And the equation is B1 plus B2 over 2, right? So 3 plus 1 over 2. So I can actually, what is 3 plus 1 over 2? Help me here. I can't think in front of a crowd. 3 plus 1 over 2. Thank you. And then 3 minus 1 over 2. 1. Thank you. There you go. Here's the linear combination. And that should be equal to 3 and 1. I have a linear combination, so linearly dependent. And I can do all this in a kind of a nicer handwriting. Okay? So these are linearly dependent. Now, how do we know that these are linearly independent? Well, we know that these two obviously span R2. This belong in R2, so we can like immediately see it. Okay? If you're kind of well trained in the art of seeing a span, which you will be by the end of the class. Okay, that's great. Now I can also say the following, right? I said that these two, if I add them together, equals the third, but I can also write it slightly different. I can say that 2 times 1, 1, plus 1 minus 1 minus 3 and 1 equals 0. Can I say that? I just moved it from the right-hand side of the equation to the left-hand right, and then left-hand side, and then added a negative. So the sum of this linear combination of vectors equals 0. And that leads me to a new definition, definition 2 of linear dependence, that sometimes it's easier to deal with. With all this AIJ that we had before, that I got you all confused, here's a new definition. A set of vectors, alpha 1 all the way to alpha n, just to be consistent. So here's is going to show up next year. And I'm going to say, oh, do you know what these m's are?
Yes.
That's a mistake of the past. Soon to be corrected. And last time I did this, Anna just like burst in laughter here on the floor. She was just like, and nobody really got what it means.
I was crying.
She was crying. Okay. So it is a mistake of the past. All right. So here's the definition. A set of vectors, this set of vectors are linearly dependent if there is a set of, sorry, I'm gonna start from scratch. Okay, there you go. Okay, a set of vectors is linearly dependent if there is these coefficients such that if I do a linear combination of all these vectors, I can actually reach 0. Now, there is some restriction, because if I set all the alphas to be 0, that's a problem. That's true, right? But it's a problem. So at least one should not be 0. Okay? At least one. Okay? As long as not all AIs are 0. That is another definition of linear dependence. So give me vectors. 1, 2, 3, 4, 7 vectors. Okay, now I need to find a coefficient that if I sum them together, I would get a 0 vector. If it is a 0 vector, linearly dependent. Now we have a test. And that test can be solved via Gaussian elimination. Not the game, but the algorithm. Yeah. One of AI was?
So if one of the AI vectors were all 0, then the entire thing would be linearly dependent.
Okay, so one of the AIs, no, so it cannot be also 0, right? So I guess the definition also, the AIs are not all zeros, okay? So we add it as long as, and then also AI, all these vectors are not equal the 0 vector, okay? Because then it's degenerate, okay? Not all of them could be 0. Okay. Okay. So that is another definition. This definition is very useful. Yes. Yeah, 0 is linearly dependent, yeah. Yeah. So it's a special case, a 0 case, right? Everything, we're going to talk about something called a null space, and 0 is always the trivial null space, the 0 vector, which is always can be done, but we're going to look for non-trivial cases. Yes?
So you're saying as long as not all alpha I are 0?
Yeah, not all alpha I and AI. Yes, alpha. Thank you. Wow, so many mistakes in a single slide. Beautiful. We solved it together. Wow. Look at that, how it's going to look next year. Maybe I'll fix it. It's too much. Okay, so here's another definition. a completely different topic. We're going to talk about linear independence. Completely different topic. And the definition of linear independence is a set of vectors, A1 all the way to AM, are linearly independent if they're not dependent. Okay? That's really the definition. If they're not dependent, then they're independent. Okay? So if you can't find a sum of them that would reach 0, then that means that they're independent. Okay? Are these linearly dependent? What do you think? Yes. Why? Because pi and square root of 2, albeit they are non-rational numbers, are still in R2 and can be reached by some multiplication of the first vector with a sum, again, another scaling factor of the second vector. Okay, there is a solution because they live in R2 and the first two span R2. So we can have a solution. So they're linearly dependent. Yes. Ooh, that's a nice theorem. Let's take a look at this theorem. And now I'm going to focus in the middle. If the columns of the matrix A are linearly dependent, what does it mean again? Now I can find some linear combination, then that will sum to 0, right? That's what it means. Then AX equal B does not have a unique solution. Whoa, wow. Remember tomography? We could have solved it. We could have known. We could have known. Now, what does it mean not having a unique solution? Does it mean that there's no solution? Not necessarily. It means that if there is a solution, there's many of them. Or there could be that there's no solution. But in neither case, it's not going to be just a single solution. There's no unique one. Okay? Interesting. You know what? We're going to prove this. Now, this is quite complicated proof. All right? I'm going to use a lot of symbols and stuff. So I want you to really pay attention here. Okay? Okay, ready? Now. You know what are these? Mistakes from the past. That's right. I'm not going to prove it for Rn. We're just going to pick for R3. Okay? And we're going to try to prove this. This is not, like, oh, wow, not having a unique solution. Whoa, how do you go about it? It's like, Extremely powerful, by the way. So we're going to prove for R3. What do we know? Look at the theorem. If the columns of the matrix A are linearly dependent, then what do we know? The columns of A are linearly dependent. That's what we know. Okay? So we know that the columns of A are linearly dependent. What do we need to show? There's what? That there's more than one solution, right? Or no solution, right? That's what we need to show. Okay. There you go. So how do we go about it? The what? Well, remember when we did like this thing where we said, oh, let's pick an explicit thing and then just run with it? Okay, we know, let's say we say, oh, let's say there's no solution. Like find an x that there's no solution. Well, there's no solution. Okay, so then it's done. But what about the case where there is a solution? So we pick a specific solution. And then what we need to show is that there's another one. If there's another one, then it's not unique. Does that make sense? So that's what we're going to do. We're going to pick a solution and then show that if there is a solution, if that solution is right, then there's another one. If we find another one, then it's not unique. Okay? That's how we're going to go about this proof. So pick some specific solution, x star, and show that there's another one, like x dagger or something like that, that also satisfies the same equations. If we do that, then it's not unique. Okay? All right, so what we're going to start is, let's pick x star. X star is the solution. Ax star equals b. Okay? That we know it's true, because we picked it. X star equals b. And then A is A1, A2, and A3, right? Okay. All right, what is the linear dependence definition? Linear dependent definition 2. There is a sum, right? Linear combination of the columns of the matrix A that would lead me to a zero vector. So there is some alpha 1 times A1 plus alpha 2 times A2 plus alpha 3 times A3 that is equal 0 vector. Okay? That's what it means. Now I can also write it this way, right? This is A times alpha 1, alpha 2, alpha 3, which I'm going to now define as the vector alpha equals 0. Can I write it that way? Like this, like that. Like this, like that. Like this, like that. Okay, yeah, I can. That's exactly what A times vector alpha means. That's a very interesting thing. A1, A2, and A3, the vectors are non-zero vectors, right? Alpha 1, alpha 2, alpha 3 are non-zero, right? All of them. Not all of them can be 0. And it still results in a 0. So like you take some matrix, multiply by some vector, and it comes out to be 0. And you're not multiplying by zeros. That's an interesting property of matrices. Like, is that possible even? Yeah, obviously it is possible. But that's kind of the output. This is really what it says. This is what it says, that there is some alpha 1, alpha 2, alpha 3, and all of them 0, such that when I combine them, I get a 0 vector. And I guess I should, just for consistency, do that. Okay, interesting. That also means that A times alpha equals 0. Okay. So does it help me to find a new solution? I know that AX equals B. I know that A times alpha equals 0. Can I find a new solution for some other AX, let's say AX dagger, that equals B? That is not X star. Can I find another solution? A times X star equals B. A times alpha equals 0. What about A times 2 alpha? What's that? Okay. What about A times X star? That's B. If I add 0 to B, what do I get? I get a B. This is linear. If you add before, add after, doesn't matter. Right? Adding before or adding after, you do the multiplication, doesn't matter in linear systems. Can you find any solution now? I can find a lot of them. Let's do that. Here's the I want you to think about it, but here's the deal. Let's say x dagger equal x star plus that vector alpha. Is that a new vector? Alpha is not 0, so it's a new vector, right? I've got new numbers, set of numbers. New set of numbers, now x dagger. What is ax dagger? It's a times x star plus alpha. Can I open those brackets? I get a times x star plus a times alpha. What is that? 0. What is that? B. It's b plus 0. I found another solution. X star plus beta plus alpha. You know, x star times 3 times alpha is also. X star times 4 times, you know, that's where the infinite solution comes in. I found some solution that any multiplication of alpha, if I add to some vector, you know, it still be the same result. It's not going to change. Whoa. I can add something to a vector, and when I multiply a times it, the matrix will not see it. The matrix will spit the same thing. Isn't that crazy? Matrix. It basically, alpha is invisible. The direction of alpha is invisible to the matrix. We're going to talk about, it's going to be called a null space. We're going to talk about it later, but when I mention that, because it doesn't have to be just a single vector. It doesn't have to be one dimensional. It could be more. So we'll talk about that. But just wanted to give you the concept. This is not a trivial thing. Doesn't happen for scalars, only for matrices. Now that's also a cool thing. Because let's say I have ax equal b, right? Like I need to go from one place to another, right? Using my Tesla car, you know, whatever. Like a self-driving car, whatever, self-driving car. So pretty much my x star is what I need to apply in terms of, you know, left, right, you know, gas, on, off, brakes and stuff in order to reach from one point to one point to one other point. What it really means is that I can add to it some other value that I will still reach the same solution. So maybe by adding those, I can like minimize the number of brakes that I'm making. Or maybe I can minimize the number, you know, times I press on the gas or the turns, right? So I can optimize. I can get better solutions. The fact that I have infinite solutions is actually a good thing, and I can see that now. And I know actually, you know, how can I add that and not change the result? That's pretty cool.
Wow.
I know, right? So X star is a different solution. Yeah. Yes. We're actually going to, I'm not going to prove it. I'm going to prove it by telling you, oh, if you want to prove it, then just do the multiplication stuff, and then you'll see that it is. Yeah, absolutely. It's a linear system, so it is distributive. And it's also homogeneous. It's also homogeneous. Why? Because it's linear. So homogeneous and distributive. Let's do a question. Ready? Let's get you all woken up for our next transformative part of the lecture. In words, we have ax equal b. You do Gaussian elimination using some form of, you know, this augmented matrix, and you get that solution where star could be any number. And you want to pick the most accurate statement. 1 minute. This is taken from Fall 22 Quest. Don't talk. Do it yourself. Okay, 180. Let's do 20, 19, 18, something after that. 15, 10, 9, 8, 7, 6, 4, 3, 2, 1, and the results. Okay, 52% saying that A equal B has no solution. The next one saying that all of the above. And then the rest saying that AX equals 0 has infinite solution and the columns of A are linearly dependent. That is very interesting. What I want you is to talk now to your neighbors and try to convince them why your solution is the right one. Come on, do that. You got 1 minute. That's a good one, huh? Oh. Oh. By the way, I want to apologize for all the folks that want to rest, do some other homework, and I'm disturbing them. So I truly apologize. I still thank you for coming here today. Still thank you for coming here today. Okay, ready? 20.
17. 15. 12. 9.
Come on, vote.
5.
4, 3, 2, 1. I'm really hoping for like a good solution here. Oh, come on, only 109 voted.
Oh, it's combined.
There's like
The
270
answer
before. Come on, do
combined.
it. Come on, vote. More,
It was
153,
teamwork,
161.
I guess.
Okay, I'm going to show it.
Oh,
interesting. Okay, so the winner is all the above with a very slight majority. Kind of looks like the US election. That you don't know, have no idea what's going to happen. Interesting. Okay. So everybody that voted for the Green Party, you got it the most right. Everybody else got it somewhat right, but the most right was all of the above. Okay? And let's go over the solution because this is useful. Let's see the first one. When you stare at this type of a Gaussian, augmented matrix in row echelon form, then what you see here, oh, there's a 0 on the diagonal, right? So it could be that there is either infinite solutions or no solutions. How do we know whether there's infinite or no solution? You look at the vector result, and if there is a value, oh, that can never happen, right? So something 0 times x1 plus 0 times x2, 0 times x3, 0 times x4 equals 4, not possible. Hence, A equals B has no solution. But here was the tricky part. What about AX equals 0 has infinite solution? Well, what if I put zeros here? Will that be okay? Yeah? Now there's infinite solutions that I can achieve. What is the solution? x4 equals 0, x equals 0, x3 equals 0, x2 can be anything, and then x1 equals 0, right? So x2 can be anything, hence there is infinite solutions. Okay, so that is also true. Okay? Whenever you see, just ignore this part always, ignore this one, and then you can figure out if there is infinite solutions. Then you look and see if it fits. If it doesn't fit, then there isn't a solution. But remember, there's either infinite or no. These are very similar cases depending on what the result is, what is the vector B is, and then if it's a unique solution, well, then you have to have this diagonal full. Okay? So saying that, this is true. What about the columns of A are linearly dependent? The columns of A are linearly dependent. Yeah, it's absolutely true, right? Because there is some linear combination of the columns of A that would reach 0, right? There is some linear combination of the columns of A that would reach the vector 0 because B and C is the same. It's saying the same thing, B and C. Does that make sense? Yes?
So we said that for the theorem, we said that it was like if they are linearly dependent, then they don't have a unique solution.
Don't have a unique solution.
Can we use it backwards? So if there's no unique solution, then they are linearly dependent?
Yes. Yeah. It goes back and forth. Yeah. So, of course, then all of the above are true. Okay? Does that make sense? All right. Let's talk about matrix transformation. Some of you may find it funny. Yeah. The solution, whether there is a solution or there's no solution depends on the vector B. It doesn't depend on A. Right? If A is linearly, if A has linearly dependent rows or columns, by the way, it doesn't matter. Like you'll see that. Then you can express its columns as a sum to 0. Right? That is true. Now, depending on B, it's either you have infinite solutions or not, or no solution at all. Right? That depends on the vector B. I'll take one last question, yeah. Oh, sorry. For part B, AX equals 0 has infinite solutions. Well, I could find infinite solutions actually. Yeah, you can set x1 to be something else, right? So, it depends on B. Once you set B, then you can set x1 to be that. Does that make sense? So let's say I pick B, x2 to be, I don't know, 3 or 1. Let's say 1. Then x1 should be minus 1. Okay. All right. So some of you may find this funny. Some of you don't get it. Hopefully, by the end of class, you'll find it funny. Okay? Let's see. Remember, when we think about matrix operations, AX equal B, we take some vector x. We take A, you multiply A by x, and you get new vector B. X has been transformed into B. It's a transformation. So we can think about that in that context. So let's think about this example. What is this example? The matrix 1, 0, 0, minus 1 times x1, x2 does that. Okay? What is this transformation? Well, let's try to do it. Let's pick one. Let's pick an x. Here's an x. What is the result after applying A times x? x1, the first index stays the same. x2 is being inverted, right? Like just not inverted, but negative sign. Okay, so it goes down there. What is this operation? Let me give you a hint. Oh, what's going on? What's going on?
I've been working on this reflection.
Someone's reflection.
The reflection.
There's a reflection of the man's face.
The reflection.
There's a reflection.
Zoom in on the mirror.
You can see a reflection.
Do you hear it? What is it? Wow. Nice, you guessed. It's a reflection of this vector along the x-axis. Okay, that's what it is. Along the horizontal axis, that's a reflection. And what if I take this vector, where it's going to be ending up at? Right? Negative y, right? The y-axis is being inverted. And what about this one? And what if I have a mountain? And if I have a mountain that it's the end of, you draw it, and so all the vectors that end up at the edges of the mountain. What's going to happen to all these vectors? They're going to be reflected, so you get a reflection. Yeah, that's why it's called a reflection. Right? It's like a lake. You stare at this, oh wow. Okay, so this is one type of a transformation. You can think of it from a geometrical way that is being reflected. That's one way that matrix operate. They reflect stuff. They also do other stuff. For example, here's, whoa, what is this? Sines and cosines, sounds like high school or like middle school. Whatever. What does this do? What does this matrix do? Cosine, sine, minus sine, cosine. Let's try it. Okay, you stare at this long enough and go like, I don't know what it does. Like it's too complicated. So what you do is you start with an example that kind of make it easy. So let's pick a vector. Okay, let's pick the vector 1, 0 and see what happens. Okay? If I take the vector of 1, 0 and I multiply like this, like that, like this, like that, I get cosine and sine of theta, right? Like this, like that, this multiplies by 1, this multiplied by 0, I get cosine. Like this, like that. Sine multiplied by 1, cosine multiplied by 0, I get sine. Okay? Hold on. So I'm going to start with 1, 0. This is the vector 1, 0. What is this vector? Cosine theta and sine theta. So the x-axis is cosine theta, the y-axis is sine theta. It's effectively a rotation of that matrix in counterclockwise. Okay, when you have that form, it's in counterclockwise, and it's a rotation by theta. So this matrix, when you multiply it by some vector, it rotates it around the center axis. Can you see that? What if theta was 0? Sorry, not 0. Theta was 90 degrees. Then what would you get? What would be cosine theta? Cosine theta of cosine of 90? 0. So x-axis would be 0. Sine theta would be 1, right? So 90 degrees. That kind of makes sense. It will be this vector. And theta would be 90 degrees. So it rotated 90 degrees. Does that make sense? What if theta was 180 degrees? Whatever. It'll flip to the other side. You got the point. It's a rotation matrix. It's a rotation counterclockwise. Okay, counterclockwise. Now, what if I take this theta and I take this vector now? I have this vector and I multiply this matrix times this vector. What I'm going to get? it's going to rotate by more theta. And then if I multiply it again, it's going to rotate again. If I multiply it again, it's going to rotate again. This is a clock. Analog clock, like the one over there that's rotating all the time for me. Kind of I'm seeing the end of the class. Applying all these rotation matrices. Does that make sense? You can do this. You can do this again. Like you can do that trick. So you get that? You get that? Ah, that's funny, right? Because it's like this is a rotation matrix for 90 degrees, and you write like A1, A2 like rotated 90 degrees. Funny. I told you, hopefully you'll find it funny by the end. And this one has the minus here, so it's actually clockwise rotation. That's why it's clockwise rotation. Okay? How do you know? You check. By the way, if somebody tells you, oh, this is counterclockwise, and goes like, no, it's clockwise. And go like, this is counterclockwise. You go, no, it's clockwise because the minus, I remember. Just check. Put some value. See where it rotates. Does it rotate this? Does it rotate the other way? It helps. Just try it. Aww. You see this? It's my daughter and my spouse. And check out. What do you think this iPad is doing right now? It's applying rotation matrices. It is. It's just that's what it's doing. Many rotation matrices, and reevaluate those values of this matrix by applying those. That's what it's doing. It's applying all these matrix transformation. So when I'm doing that, that's rotation, And then this one, translation. I'm adding a coordinate. Oh, and guess what? Scaling. All of this is done using matrix multiplications. All of this is implemented that way. Very simple. In the homework, you're going to actually try to have create a panorama. Like you have two pictures. They don't match exactly because one of them you took with a little bit zoom, a little bit rotated, and you want to rotate and kind of adjust so you can actually stitch them together. That's what you're going to do in the homework. Pretty cool homework. Okay. There's more transformations, right? Like I can also scale something. How do I scale something? What does a diagonal matrix does? What does this do? Scales x1 by 3, scales x2 by 3. I'll get a bigger picture. Okay? The vectors are scaled. So if I had a picture of a mountain and now I scaled it, it becomes bigger. Okay? Cool. Okay, then you ask somebody, is that linear transformation, associative? Who asked that? Associative, matrix, multiplication, stuff. Who asked if matrix, vector multiplication are associative? You did. Okay. So, remember a linear transformation is when you have f of a times some vector x equals a times f of x. Means that if you scale the vector before putting it through the matrix, it's the same as putting it first through the matrix, through the system, and then scaling it afterward. Okay, that's homogeneity. This is distributivity. You take two vectors, you add them together, push it through a system. It's the same as taking one vector, push through the system, another vector push through the system, and then add the result. That's distributivity. Together, they result in a superposition. Superposition is both homogeneity and distributivity. And I'm claiming that matrix vector multiplication satisfy linear transformations. How do you go about improving? Well, let me argue that A times AX is the same as, alpha X is the same as alpha times AX. How do you go improve that? you can go and expand the coefficients of A, and based on this scalar matrix multiplication that we defined before, and vector and matrix vector multiplication that we defined before, you can see that this is the same. You can just go and write that explicitly. Okay? The same thing you can do here. You can write that explicitly as well. Hence, they satisfy that. And so these are linear transformations. Okay? So what we're going to do next time, like again, tomorrow there was no lecture, remember? It's canceled. But there's still discussion. And no quiz. No. A quiz, yeah. And Thursday, what we're going to do is I'm going to show you a way to use matrices to represent basically a state of a system and how to evolve that state.
No,
Okay.
if you want.
Oh, no.
No?
No, I won't. You know what we're going to do on Thursday? Because you have lab next week, and one of the things you're going to do in lab on Monday, starts Monday?
Monday, next
Yeah.
week.
Then you have to like assemble a few circuits and stuff. But we haven't really talked to you about circuits. So we thought we're going to take a break a little bit from linear algebra and then talk a little bit about circuits so you know what you're going to be doing in the lab. And then next week, on Tuesday, we're going to continue this topic. But on Thursday, slightly new topic, which is circuits. So don't miss it out. It's going to be awesome.
Yeah. Good lecture.